Next, let's look at some examples of left-hand and right-hand Riemann sums. So our first example is to compute the Riemann sum for f of x is equal to x squared. So estimate the area under f of x from x is equal to 0 to x is equal to 2 using a left and right hand Riemann sum with 4 subintervals. So if we graph this, we have, so here the output is 1, and here the output is 4, 2, 1, 0.5, and 1.5. So we're going to use 4 subintervals. So the left-hand Riemann sum is going to look something like this. 0 area, some area here, some area here, and some area there. So the left-hand Riemann sum will look something like that. So the left-hand Riemann sum will utilize the x values 0, 0.5, 1, and 1.5. So we can also think of the x-axis 0 to 2, 1, 0.5, 1.5. So there's the x-axis. The left-hand Riemann sum, we're going to use the left endpoints like that. So the left-hand Riemann sum with 4 endpoints is going to be f of 0 delta x plus f of 0.5 delta x plus f of 1 times delta x plus f of 1.5 times delta x. So that's what the formula for the left-hand Riemann sum will give you. Now delta x is equal to 0.5, and each term has a delta x, so I can pull that out. So the left-hand Riemann sum is going to equal, okay, so here we have y is equal to x squared, so I have 0.5, that's my delta x, and then times the quantity f of 0, well f of 0 is 0, plus f of 0.5, so 1/2 squared is 1/4, so we have plus 0.25, plus, so that's f of 0.5, f of 1 is going to be 1, and then f of 1.5, so 1.5 squared is 2.25, just double checked, like that. So the left-hand Riemann sum is 1/2 times the quantity 0 plus 1/4 plus 1 plus 2 1/4. So here we have 2.5 plus 1 is 3.5. 3.5 times 1/2 is 1.75. So the left-hand Riemann sum is 1.75. Now if we redo this with the right-hand Riemann sum, so let me clear some space. Let's clear some space at the top. So in this case, we're going to have the right endpoints. So I'm going to use the right endpoint for the first subinterval, the right endpoint for the second subinterval, the right endpoint for the third subinterval, and the right endpoint for the fourth subinterval. Notice that this is like sliding the second rectangle of the left-hand Riemann sum 1 to the left, sliding the third rectangle for the left-hand Riemann sum 1 to the left, sliding the fourth rectangle for the left-hand Riemann sum 1 to the left, and then adding a new rectangle with height equal to f of b. So for the right-hand Riemann sum, so here's the left-hand points. So for the right-hand points, we're going to use 0.5, that's the right endpoint of the first interval, 1, 1.5, and 2. So those are my right-hand points. So the right-hand Riemann sum is going to be f of 0.5 times delta x plus f of 1 times delta x plus f of 1.5 times delta x, and then plus f of 2 times delta x. Now notice that these 3 points are in common. Right? So the points 0.5, 1, 1.5 are in common between the two Riemann sums. So the left-hand one also has f of 0, and the right-hand one also has f of 2. So the right-hand Riemann sum is going to equal delta x, which is 0.5, and then times the quantity. Well, f of 0.5 was 0.25, f of 1 was 1, f of 1.5 was 2.25, and f of 2 is 4. So now when I add all this together, I get 3.5 plus 4 is 7.5, divided by 2 is 3.75. And so the right-hand Riemann sum is equal to 3.75. Now, the function x squared is an increasing function. So f of x equals x squared is increasing. Because it's an increasing function, the left-hand Riemann sum is less than the true area, and the right-hand Riemann sum is greater than the true area. That means that 1.75 is less than or equal to the true area, which is less than or equal to 3.75. So the true area is in between those two estimates. If it's not increasing, that's not true. If it's not increasing or decreasing, you can't say anything, right? If it's going up and down, you can have both of them being overestimates or both being underestimates, depending on what the case may be. Only when you have an increasing or decreasing function can you say something like this. Now also, let's look at the difference. Let's look at the right-hand Riemann sum minus the left-hand Riemann sum. So notice that the right-hand Riemann sum minus the left-hand Riemann sum is 3.75 minus 1.75, which is equal to 2. Now, as it turns out, there's a formula for this, as we saw, and it should be equal to f of b, so that's f of 2 minus f of a, and then all times delta x. Well, f of 2 is 4, and f of 0 is 0, and delta x is 0.5. So the formula works. A half times 4 is 2. So the difference between the two Riemann sums is equal to 2. Now suppose I want to know how many intervals I should use in order to get a certain accuracy for the area. So suppose I want the estimate to be within 0.01 of the actual area. So the way to do this is to basically require the right-hand sum minus the left-hand sum to equal 0.01. Because it's an increasing function, we know that the left-hand sum is less than or equal to the true area, less than or equal to the right-hand sum. Actually, if you really want the estimate to be within 0.01, what you could do is, here's some problem solving. Well, the right-hand Riemann sum's up here. Let's say the left-hand Riemann sum comes out down here. Now, if you choose a point halfway in between, you know that the true area is somewhere between the low end point and the high end point, right? The true area is somewhere within here. So if you use this midpoint as your estimate, that will guarantee, and you want your estimate to be within 0.01, you can actually probably choose n so that the distance between the right hand and the left hand Riemann sum is 0.02. So if you choose the point right between, let's say the actual value turns out to be up there, regardless of where the actual value is, it's going to be within 0.01 of the average of the left hand and the right hand Riemann sums. So if you want an estimate that's within 0.01, you could set the distance to be 0.02 and then say, okay, let's take the average of the left hand and Riemann sum, left hand and right hand. We're going to do it a slightly different way. We're going to say that the distance between the right hand Riemann sum and the left hand Riemann sum is 0.01. So even if the x comes out here, it's no more than 0.01 to either the left hand and Riemann or the right hand. So depending on which way you want to do it, you can do an estimate any way, right? They're estimates, so it depends on what you're looking for. So let's just take it this way. So let's say that the distance between the right hand and the left hand Riemann sum is 0.01. So how many subintervals do we need in order to make the distance between the left hand and the right hand Riemann sum equal to 0.01? Well, the right hand Riemann sum minus the left hand Riemann sum is equal to f of b minus f of a all times delta x. Now f of b is 4 and f of a is 0. So we get 4 times delta x. Delta x is b minus a over n. Now b minus a is 2, so we basically get 8 over n. So the right hand Riemann sum minus the left hand Riemann sum will be 8 divided by n. And we want this to be less than or equal to 0.01. So that means 8 has to be less than or equal to 0.01 times n. Multiply both sides by 100. N has to be greater than or equal to 800. So we can choose n is equal to 800, and we would use 800 subintervals, and that would guarantee that both the right hand and the left hand Riemann sums are within a distance of 0.02 to the actual area. So that's how we can use this difference formula between the left hand and the right hand Riemann sum to hone in on the accuracy when we have an increasing function or a decreasing function.